and we have seen the two problems related to the temperature, stress and strain. Okay, so today we have discussed the more concept of temperature, stress and strain in different conditions. Okay, so today we have seen what are the effect of temperature variation on a composite section. Okay, because in the previous lecture we have seen if temperature increase, then length of the element is increased. Okay, and decrease, then their length is decreased according to their temperature coefficient. Okay, so let's consider the composite section. Composite section means two material are combined together and react as a single element. Okay, so if we consider two material, steel and okay, so let's consider one bar which is made of steel and another material is copper. So this part of is made of a steel and this bottom one part is made of a copper. Okay, now whenever the temperature is increased, so we have seen that their length is increased according to the temperature coefficient. Okay, or thermal expansion coefficient. So steel have a different thermal expansion coefficient, copper have a different thermal expansion coefficient. So the change in length is defined by L alpha T. But here L for both the element is common. Temperature variation is also common because both are combined together. But their alpha is different. So according to their thermal coefficient, change in length is also different. Suppose if we increase their temperature from T1 to T2, so the length is obviously increased. So the increase in the steel section, suppose we have assumed that the steel coefficient is lesser than copper coefficient, means change in steel is lesser than change in the copper length. Okay, so change in length of a steel section is something like this. Okay, and change in length in the copper section is something like this, higher. Okay, now then what happen? Both the material are combined together, so react as a single element. So there, but due to the different thermal coefficient, the change in length is different. But both are combined together, so that what happens? This copper element is apply the pull force on the steel element in these directions, and the steel section is apply the push force on the copper element, and they will try to extend over same deformations. They will undergo the same deformations like this. Okay, because both the material are combined together. So if we see that, so change in length for both the material is same under the effect of temperature variations. Okay, so we say that due to the temperature changes, change in the steel section is equal to change in this copper section. Okay, now what are the change in the steel sections? So up to the here they will increase their length due to the temperatures, and then after this changes is due to the pull force by this other element. Okay, so change in the steel section due to the temperature plus change in the steel sections due to the stresses by other element. Now what happened in the expansion is up to here, but actual expansions due to the composite section is this. So the expansion of the copper sections due to the temperature is this, and out of this minus the contraction of that copper sections due to the composite effect, means due to the other elements which will try to pull force, and it will keep the same deformations under the change of the temperature. Okay, so this is the effect of temperature in both the element, and this is the effect is due to the composite section effect. Okay, so here delta st is the free expansion here, and delta s stresses is additionally expansion due to composite section. Okay, now if we We write these equations. So change in the steel due to temperature minus change in this copper due to the temperatures is equal to, okay, sorry, change in this copper due to the temperature minus change in this steel due to the temperatures, means this move the right side, and this due to the composite effect move the left side. So delta S change in the steels due to the composite section plus change in this copper due to the composite section. Okay, now change in these copper sections and steel sections due to the steel temperature change is defined by these equations. So here we write the L alpha T, but here alpha is the for copper and minus L alpha T, but here alpha is for steel. Okay. Now length and temperature variation is common for both the material, so it's remain constant. Only changes their thermal expansion, thermal coefficient. Okay. Now change in this steel and copper due to the composite effect is given by PL by A. Okay, and plus PL by A. Now force which will apply on each other is same. So P is same, length is also same, area is maybe different. So we say that this is the area of steel and Young modulus for steel, and this is the area of copper and Young modulus of copper. So if we take the L common from both the side, so it's cancel out. Okay. So here alpha C minus alpha S into T is defined by P by A, that is the stress in this steel section. So sigma S by ES plus sigma C by EC. That is the stress in steel by Young modulus and stress in copper by Young modulus of copper. Now
Sir,
this
area.
alpha C is, yes,
Area,
force by
area.
area is stress.
Okay, okay, sir. Okay, sorry, sorry.
So here uh, we have assumed that the thermal expansions for copper is higher than steel. So we say that expansions coefficient for copper is higher than the expansions coefficient of steel. So we get this relations between the stress and the temperature variations. Here temperature variation is T and stress in the different material is defined by sigma S and sigma C. Okay. Now here whatever the force applied by copper on steel to additional expansions and whatever the force applied by the steel on copper due to the composite effect, both forces are same. So we say that the force on steel and copper are same. So pull force is equal to push force. Okay, whatever the push here for additional expansions, that is equal to the pull force for contractions. Now here this pull force is force on steel section and push force is force on copper sections. Both are same. So here area into stress in steel section, and here area of copper into stress of copper sections. So we get the stress in steel is defined by AC by AS into sigma C. So that is the relations between the stress generated in these two material according to their area difference. Okay, so we have used these two equations, these two relations. This is the define the relations between the temperature variation and stress value, and this is show the stress relations between these composite sections according to their area difference. Okay, so we have consider these two relationship and solve the difference problem. Okay, so let's see the problem so you can get the clear idea about this temperature effect on a composite section. Okay.
सर उसमें जो
Yes,
स्टील हमने एग्जांपल स्टील और कॉपर का लिया, लेकिन कोई भी हो सकता है मतलब.
yes, yes. Any material is there,
ओके
but here you have to define this their thermal expansions, if whichever is higher, then you have to put here, because according to their difference, the stress is generated. If both the material have a same thermal expansions coefficient, so their expansion is same, so no any additional stress is
Yes, sir.
generated.
मतलब जिसका और उसका पहले लेना है.
Yes. So now consider the problem. So we have two sections like this. This one is the bigger tube. Okay. This is the steel section. Is 1257.1 mm square. Out of the steel sections, at the core part of this sections, here one copper tube is composite with that. This one. Okay. So this is the copper sections and remaining portion is steel sections. So area of that copper section is also defined 706.9 mm square. That is given to you. Okay. Here Young modulus for steel section is 2 into 10 raised to 5 Newton per mm square. That is given to you. And Young modulus for copper section is 1 into 10 raised to 5 Newton per mm square. That is given to you. The thermal expansions coefficient for steel section is 11 into 10 raised to minus 6 per degree Kelvin. Okay. And here thermal expansions coefficient for copper is 17.10 raised to minus 6 per Kelvin changes. Okay. Now here the temperature changes is you have to consider the 50 Kelvin. Means whatever the initial temperature is there, so out of that 50 Kelvin is changes. Okay. So per changes in Kelvin temperatures, the thermal expansion is given to you. So you have to find out force on steel and copper. Okay. What are the forces generated on steel and copper due to their composite effect, due to the change in this temperature? Okay. So we have considered the first equations, that is alpha c, because alpha c is greater than steel section, alpha s. So alpha c minus alpha s into T is defined by sigma s by es plus sigma c by ec. That is our first relations between the temperature changes and stresses generated in the different material. Okay. So if we put the value here, so 17 into 10 raised to minus 6 minus 11 into 10 raised to minus 6. Temperature difference is 50 Kelvin. Okay. Now stress in the steel section is find out, because from the stress, if we find out the stress, so we can easily find out the forces. Area is given. Okay. So first of all, we have find out the stress, and then after from the stress, we have find out the force. So stress is unknown. Es value is given 2 into 10 raised to 5 plus stress of copper is also unknown, and their E value is given into 10 raised to 5. Okay. If you simplify these equations, so you get sigma S plus 2 sigma C is 60. It is our equation number 1. Okay. Now we use the second relations. The force on both the material are same, because force applied by copper on steel is equal to the force by steel on copper. Okay. So if no external force, then force in steel is equal to force in copper. Okay. So we say that area of steel into stress in steel is equal to force. So stress in copper into area of copper. Okay. So both the area is given. So if you put here the area, so you get the relation between the stress of steel is equal to 0.56 times the stress in copper. That is the second equation. Okay. Now from the equation number 1 and 2, two unknown and two equations, so you can easily find out the unknown forces. So here we get the stress in this copper is 23.42 Newton per mm square. Now once we find out the stress value, so we can easily find out the force, because force in copper is defined by stress into area. Okay, so stress is already find out 23.42. Area of copper is given 706.9. Okay, so we get the force is 6561650 Newton. Okay, and that is the answer, because whatever the force applied by copper on steel is equal to the steel on copper. So you can also finding out the stress on the steel section, and then find out the forces is equal to area, steel stresses and area of this steel. So you can also get the same answer.
सर हम सर इक्वेशन 2 फाइंड ना करें और इक्वेशन 1 में सिग्मा मतलब सिग्मा एस की जगह एफ बाई एस और सिग्मा सी की जगह एफ बाई ए सी डाल के
यस,
सीधा फाइंड कर दे फोर्स तो चलेगा।
यस, 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 वो तो कंबाइन ही किया ना आपने, क्या किया सिंपली,
लेकिन ओके सर।
but they are the composite effect of a different material due to the temperature variations. Okay, so in this way you have to deal with the composite section. Okay, now we have studied the different constant related to the stress and strain property of a different material, and is known as the elastic constant. So we know that the Poisson ratio is defined as lateral strain to linear strain. Means strain in y direction by strain in x directions. Okay, so means if you have any element and if you apply the forces sigma x stress in these directions, so whatever the change in length in these longitudinal directions and the change in length in these lateral directions, so the relations between the strain in longitudinal directions and strain in the lateral directions due to the external force or external strain is known as the Poisson ratio. Okay, if we consider any material or any section like this, the length is L, the radius is, okay, and if we apply the forces in these directions, so under the effect of these forces, we have a linear strain, means the length is increased, their weight and also decrease, okay, because the Poisson's effect. So here strain in x directions is defined by change in length by original length. Strain in y directions is defined by, if you consider this is y directions, so change in this diameter by change in the depth by original depth, and strain in z directions is defined by change in the width divided by original width b. Okay, if we consider the volume of that section, so the volume is the L into B into D, and if we find out the volume after the applying this force, so V dash is defined by new volume V dash. Now we have considered the new length, so new length is change in length is delta L, so new length is L plus delta L. Now new width, so length is increased but their width is decreased due to the Poisson effect, so B minus delta B, and the depth is also decreased, so D minus delta D. So if we find out the change in the volume, so V minus V dash, no, sorry, that is the change in their volume. So we get B into D delta L minus D into L delta B minus L into V delta D. Okay. So if we divide this, change in the volume by original volume is known as the volumetric strain. Here we have considered any individual directions, that is change in length for original length. So we get the longitudinal strain. Here change in the depth divided by original depth. So we get the strain in the depth, means y directions. Same way, if you find out the change in the volume by original volume, so is known as the volumetric strain. Okay.
सर वॉल्यूम कांस्टेंट नहीं रहेगा?
No, volume not constant, because whatever change in the length is equal, not change in the width or depth. They depend on the Poisson ratio. Here, suppose 1 unit is increase in length, so not 1 unit decrease in the depth or width, okay? Because they are not a same amount of increase or decrease.
Okay, sir. Okay.
So change in the length is there something. So here we get delta L by L minus delta B by B minus delta D by D. Okay. If we divide these equations by LBD, so every term is divided by LBD. So we get this. So now is defined as the volumetric strain. So delta V by V is equal to, this is the strain in x directions minus strain in y direction minus strain in z directions. Okay. But according to the Poisson ratio, we have said that Poisson ratio is defined by mu. So y by x. So we say that strain in x direction is 1 by, sorry, is defined by 1 by m. Poisson ratio is mu. Okay. So if you find out the y, mu into epsilon x. So if you find out the any another direction strain, so you have to multiply with Poisson ratio and longitudinal strain. So here instead of Ey strain in y and z directions, we have put in terms of x. So minus mu into strain in x minus mu into strain in x. Okay. So we get epsilon x, that is strain in x directions, 1 minus 2 mu. That is the volumetric strain. Now that is the effect due to the only one forces, which is in longitudinal directions. But in practically, the stress is acting simultaneously from the multiple directions. Okay. So if we consider any element like this, okay, the force in x directions, force in y directions, and force in z directions. Okay. If both the forces are act simultaneously due to the single direction forces, so if you find out the x direction strain, so their effect due to this direction forces in this longitudinal directions. Now we have find out this change in this x directions due to this px. So px is act in the x directions, so their length is increased, so it's considered positive, and this given by the strain in x directions. So strain is stress by Young modulus in x directions. Okay, that is the effect of px in x directions. Now also the effect of Py in x directions. Due to this Py, the length of the x direction is decreased. So minus mu into stress in y directions into E. And due to the effect of this Pz forces, Pz effect in x direction. So also x is reduced due to this Pz. So minus mu stress in z directions by E. Okay. So that is the effect of x direction forces, that is the effect of y direction forces, and effect of z direction forces in x directions. Means due to this x, length is increased, but due to this py and pz, the length in x direction is decreased. So ultimate effect under these three direction forces is this. Same way, you can also write the strain in y direction is stress in y by Young modulus. So strain in y directions minus mu strain in x direction minus Poisson's ratio times strain in z direction by E. Okay, and we also write down the strain in z directions. So due to the strain in z directions, that length is increased in z direction, but due to the other two directions, effect is opposite. So mu times strain in x minus mu times strain in y. Okay. Same way here, if you apply the force in these longitudinal directions, so longitudinal length is increased, but other length is decreased. So same way here, if you find out only the effect of single direction forces, so this one in x directions, but any forces act in y or z directions, so they have also produced the effect in longitudinal directions. Okay, so that is the effect of y, all these three direction effect in a single directions. Now here, if any stress is compressive nature, so you have to opposite sign put here. Okay, so it's become the plus. So let's consider one example. Okay, we have considered one steel section like this one. The length is 200 mm, their width is 20, the depth is also 20. Okay, now here force is act 40 kilonewton. So you have to find out the change in this volume under the effect of this 40 kilonewton tensile force. Here you have to consider the value of E is 2 into 10 raised to 5 Newton per mm square. Okay. So for finding out the change in this volume, so we know the equation for change in the volume, that is given by volumetric strain, is epsilon x 1 minus 2 mu. Okay. So first of all, we have find out the strain in x directions. So strain in x direction is given by change in the length by original length in x directions. Okay, so is equal to stress in x by E. consider the 1 meter length of the bar and apply these forces, so change in the length is 4.88 into 10 raised to minus 4 meter per unit length. That is the strain in x directions. Okay. Here mu value is also given to you. That is the 0.3. Okay, young Poisson ratio. Okay. So now find out the strain in z directions or strain in y directions. So mu into strain in x directions. So mu is 0.3 and stress is 4.88 into 10 raised to minus 4. So we get 1.464 into 10 raised to minus 4. Okay. So that is represent the strain in z and y directions. Means under the effect of this 40 kilonewton, change in the width and change in the depth. Now, if 1 meter width, so under the effect of these forces, decrease width and depth is this per unit length, and increase in the longitudinal direction strain is per unit length is this. So that is the change in the length under the effect of this force in longitudinal directions, and transverse direction means this these two direction is the transverse directions. So there in that particular direction strain is this. So that is the change in the transverse directions per unit length, and that is the change in the longitudinal directions per unit length. Okay. Now we have find out the change in the volume. So here we have put the longitudinal strain. So 4.88 into 10 raised to minus 4 into 1 minus 2 mu. Mu is 0.3. Okay. Now V is the delta V. Change in the volume we want to find out. So volume is given by the length into width into depth. So 200 into 20 into 20. That is the volume. So we get the change in the volume is 15.62 mm cube. That is your answer. Okay. Or you can also find out by another method. That is, first of all, you have to find out change in the length, means new length. So new length, change in the volume is given by L plus delta L into B minus delta B and D minus delta D. Okay. Okay. That is the new volume. Okay. So V original volume minus new volume, that is the change in this volume. So that is the new volume. First of all, you have to find out the new volume, and that's for that you have to find out delta L, delta B, and delta D. Okay. So for that, you know the strain in x directions. So delta L by L, you know the strain value, that is 4.88 into 10 raised to minus 4, and you know the length, that is 200 mm. So delta L is strain in x direction into length. Same way, you have to know the strain in y directions this. So that is given by delta B by B. So you got the change in the width, strain in y direction and to width, and strain in z direction is given by delta D by D. So you got the new depth. So strain in z directions into D. Now once you find out the delta L, delta B, and delta D, so this value put in these equations. So you got the new length, new width, and new depth. And according to these three new dimensions, you got the new volume. And then after you can easily find out change in the volume. And again you got the same answer, that is 15.62. Okay. So in this way you have to find out the change in the volume under the effect of external force. Here we have considered the three-dimensional effect of any forces. In first chapter of simple stress and strain, we have find out only the change in these longitudinal directions. So now we have see the three important constant. First one is the Young modulus. It's defined by E. So Young modulus is say that stress by strain. Okay, longitudinal strain and longitudinal strain. So the ratio stress by strain is defined as the Young modulus. Second one is the bulk modulus, and is defined as the K. So bulk modulus is defined as stress by volumetric strain. Okay, here the linear strain means whatever stress is act in a particular directions, in that particular direction strain is considered. But here if you consider the volumetric strain, so is known as bulk modulus. Okay, and here volumetric strain is defined as delta V by V, change in the volume by original volume. And third one parameter is a modulus of rigidity. That is known as N. Here N is the shear strain, shear strain. Okay. If on any element any shear stresses act, shear strain is defined by 5. Okay, because if we consider any element like this, so any stresses act, so under the effect of this shear stress, the deformation is like this, and this deformation is known as the phi. Okay, due to the shear stress. So shear stress by shear strain is known as the modulus of rigidity. This stress is a longitudinal stress, means our material is section is this, so this is the stress. So it is a longitudinal stress. Longitudinal stress by longitudinal strain is Young modulus. Longitudinal stress by volumetric strain is bulk modulus, and shear stress by shear strain is modulus of rigidity. So these three important parameter related to the stress and strain. Okay. Now in any material, if any stresses act in form of the shear stress, so for equilibrium of the shear stress, balancing shear stress is always act and intensity actions at a right angle to it. Okay. So if we consider if any material or any section is this, if any shear stresses act in these directions, for balancing the shear stress at a 90-degree of this stress, always opposite stress is there. And this balancing stress is known as the complementary stress. Okay. So for any stress is tau, balancing stress is there and is known as the complementary stress. Now here remember the one thing is this relations between the linear strain and shear strain is defined as linear strain is half of that shear strain. Okay. If you have to see this relationship, so you have to follow the PDF file which you have shared in this Google Classroom. So it's very defined that what is the relations between the linear strain and shear strain. But you have to remember that linear strain is a half of the shear strain. So we say that linear strain is defined by shear strain is tau by phi. So shear strain is tau by modulus of rigidity. So 1/2 to shear stress by n. Okay. So that is the relations between the longitudinal strain and shear strain. Now we have find out the relations between this Young modulus, bulk modulus, and modulus of rigidity. So relations between the young modulus E, bulk modulus K, and shear modulus N. Okay. So if we consider any element like this, okay. So in these directions here, stress strain in x directions, strain in y direction, and strain in z direction is this. Okay. So first of all, we have seen that the linear strain is delta L by L. Okay. So here, due to the effect in these longitudinal directions, their length is increased, but due to the effect of this y and z directions, their length is decreased. So if we consider the effect of the x, y, and z direction strain, so ultimately resultant strain is defined as 1 minus 2 mu. Okay. So say that stress by E 1 minus 2 mu. That is the equation number 1. Now, volumetric strain is defined by change in the volume by original volume, okay, and defined by stress by K, bulk modulus K. So number 2. Okay. Now we say that the volume, suppose here the length is L, width is also L, and depth is also L. 3 dimension is considered as a L. Okay. So their volume is L cube. Now if we differentiate this term, so we get change in this volume is 3L square into delta L. Okay. So we get delta V by V is 3L square by L cube into delta L, because here volume is L cube. So we get change in this volume by original volume is here L square cancel out. So we get 3 delta L by L. That is the equation number 3. Okay. Now from equation number 1, 2, and 3, if you see these 3 equations, so here linear strain is there, here volumetric strain is there, sigma by K, and here changing this volume means it's also volumetric strain, sigma V is this. Delta L by L is linear strain. Okay. So from these 3 equations, we can say that here sigma by K is volumetric strain, and volumetric strain is equal to 3 delta L by L. So 3 delta L by L is defined by stress by E 1 minus 2 mu. Okay. So from these equations, you get E is equal to, here stress out 3K 1 minus 2 mu. That is the relation between the young modulus and bulk modulus. Okay. And same way, if you also define the relations between the young modulus with shear modulus is 2n 1 plus mu. You have to see this uh, derivations from the PDF file which already uploaded in classroom. Okay, so then it's self-study. You have to see the relations between the E and N. How to do this? You have to refer from this PDF file. Okay, I derive these relations between the young modulus and bulk modulus. So we get the equation number 1. And if you have to derive the relations between the young modulus and shear modulus, so it's given by this equation. Now if you compare two equations, so you get one more relations between this E, K and N, and that is the E is 9Kn. So young modulus is equal to 9 into bulk modulus shear modulus divided by plus 3K. So these three equations is define the relations between the young modulus E, bulk modulus K and shear modulus N. And out of this, if you have to find out the value of mu, because here mu is there. So if you find out the mu value, so it's given by 3K minus 2N divided by 6K plus 2N. Okay. So you have to remember this all these relations because it is useful to solve the different problem. Okay. So today we have stopped here. We have derived all these relations between E, K and N. So one simple problems on this relation is there. We just you have to put these equations. So you get the value of any another constant. Okay. So that in these relations we can discuss in the next lectures. But today we have defined this all the relations. You can refer these relations from the PDF. Okay. So today we have see how to the find out the composite effect of any element. This is this one. Okay. Composite effect under the temperature stresses and volume, and then find out the volumetric strain, and then after consider this three constants and define the relations between them. Okay, so today we have stopped here. Tomorrow we'll discuss the different problems on these relations. Okay, now we can leave the meeting.
Thank you,
Thank you,
sir.
sir.